Time is everywhere. Your alarm wakes you up, your meetings run on schedule, and when you send a message, you expect it to arrive instantly. Computers rely on time just as much. Your operating system schedules tasks, a cache entry expires after 30 seconds, and games can measure frames per second because they know what a second is. But what happens when time goes wrong? A bank withdrawal before a deposit, a DNS record refuses to update, a TLS certificate that never expires? With time being so critical, how do computers actually keep track of it? In most computers, time is being measured with quartz crystals, which are often trimmed and tuned to vibrate at 32,768 times per second at room temperature. This means any deviation from this temperature tends to change the amount of times the crystal is vibrating, causing clock drift. Clock drift is measured in parts per million, or ppm, and 1 ppm of error is about 32 seconds of drift per year. So a clock with a tolerance of 20 ppm can deviate about 0.002% from its intended vibration speed, which is about 10 minutes of drift every year. Since this much drift can be detrimental to distributed systems, we often turn to atomic clocks. Atomic clocks use the idea of atomic resonance. Briefly, this means that instead of a crystal vibrating, we are measuring atoms vibrating. One example includes cesium-133, which is used to define what a second is. Specifically, 1 second is defined as the amount of time it takes cesium-133 to oscillate about 9 billion times. Atomic clocks are the gold standard of timekeeping, with some atomic clocks having errors equivalent to 1 second every 20 million years. However, there's a limited number of atomic clocks in the world, and they tend to be big and expensive, so how do we distribute this across the world? You've probably used GPS as a means for navigation, but GPS also has the critical function of distributing atomic time. Each GPS satellite carries multiple atomic clocks which broadcast the current time across the world. Receivers can then receive multiple timestamps from these satellites and use their location to calculate the current time. But the computers we use every day don't have dedicated GPS receivers, and for good reason. There's only 31 active GPS satellites in orbit, and you need a relatively clear sky in order to receive these signals. Because of this, time servers are split up into a stratum tree. At stratum 0, you have your actual atomic clocks and GPS receivers, which have the clearest view of the current time. From there, you have stratum 1 servers, like time.google.com or time.apple.com. The closer you are to stratum 0, the closer to real time you get. Typically, our devices are at stratum 2 or 3, since they get their time from servers like time.google.com. These time servers have a name and a protocol to go along with, the Network Time Protocol, or NTP. With NTP, your device communicates with multiple NTP servers in order to figure out what the true time is. To give a concrete, simplified example, let's take a client like your phone that sends a message to an NTP server at client time 100 milliseconds. The NTP server will receive this message at server time 103, process the message, and send out a response at server time 105. Your phone then receives this server message at client time 104. Clearly something isn't right here. The NTP server sends the message at time 105, but your phone thinks it's time 104 when it receives it. So there's clock skew. Let's see how NTP adjusts the client clock. First, we want to calculate the time a request spends in the network. Visually, this is the length of the arrows. We can do this by calculating the total round-trip time and calling it delta client. Similarly, the server processing time is delta server. To get the length of the arrows, we subtract the two to get delta equals 2. We have to assume that the round trip is symmetrical, since a precise one-way trip latency requires a synchronized clock, so each one of these arrows takes 1 millisecond. Of course, these numbers are made up, so in reality the numbers won't be so small. Now for the client to figure out what the current server time is, we can take the server sent time and add the one-way request latency to get 106. So the client thinks its time is 104, when in reality it should be 106. This means our clock skew is 2, meaning we're running 2 milliseconds behind. I highly suggest rewatching that a few times in order to really understand how clock skew is calculated. I think you'll find that it's actually pretty intuitive and you would have been able to derive it yourself. Now that we have clock skew, NTP needs to adjust the client's clock. NTP slews the clock when the skew is less than 125 milliseconds, which means it gradually updates the system time to match. When the skew is greater than 125 milliseconds, it instead steps the clock, meaning it abruptly updates the system time. However, when the skew is too big, 1000 seconds by default, NTP will give up, and no update will happen. This is one of the big reasons why you need to be very alert about clocks in your distributed system. Now that you understand clock drift, take a second to think about why this code might be problematic. I'll give you a hint. Date.now returns the Unix timestamp according to the system clock. So what if NTP decides to step the clock right after the task is performed, but before the end time is calculated? In that case, your performance benchmark is very broken. To solve this, you should use a monotonic clock like performance.now, which is a clock that counts upwards from some time origin like a system boot up. Because it is always increasing, it's a much safer way of measuring performance, as NTP stepping does not affect it. In case you're curious, Coordinated Universal Time, or UTC, uses a combination of atomic time and astronomy in order to get a universal standard. I didn't cover it in this video, but let me know if you want to see a video dedicated to UTC. Thanks for watching.